So in this video we discuss about the Adder-Subtractor 4-bit Adder-Subtractor. So 4-bit Adder-Subtractor. So in this video we discuss about this. So its block diagram or circuit diagram it's look like this. So in this 4-bit Adder-Subtractor we use 4 full adders. So you all know about the full adder operation, like it's done operation for 3 bits. Means if it is a full adder, it consider 3 inputs and 2 outputs, sum and carry, and A, B, C is our inputs. So it is about our full adder operation. So in 4-bit Adder-Subtractor we use 4 full adders. There is a 4-bit, so that's why we use 4 full adders. So see, for full adder 3 inputs are there. First A0 and B0. So B0 does not given directly to the full adder. Means if you give directly means it becomes like a adder circuit only. But here we can operate it as adder and as well as subtractor also according to our application. So that's why you can give an XOR gate here in between the B0 and full adder. So what is the another one is like K. So K like is an enable pin. So if your enable pin is equal to 0, this circuit is going to be act as a adder. So whenever the enable pin is 0, it will act as a adder. Whenever the enable pin, so 1, then it act as a subtractor. Not enable pin, it's like one of the pin which can be it can be according to work as our application. So if it is value is 0, so if the K value is equal to 0, it acts as a adder. If the K value is 1, it will act like a subtractor. We can design like that. Here according to this K value, this circuit will going to be adder or subtractor. So if it is adder, we get sum and carry. So if it is subtractor, we get difference and borrow. So now see, for full adder there is a 2 inputs. One is Cin. So Cin is nothing but our K value. You can observe that. So Cin values are nothing but a K value. So again there is a for full adder the sum and the carry will be generated. Again the carry of the first full adder is going to be input for the second full adder. Then again you get sum and the carry. So again the carry, otherwise a difference. If you are performing subtractor, you get difference. Difference and borrow. So again this borrow or carry is going to be input for the third full adder. So third full adder borrow or carry is going to be input for the fourth full adder, and finally you get the C out, means final carry or borrow and 4 bit of difference or sum. So it is our block diagram. So just like the adder circuit, but only difference is we can apply the XOR gate here by giving input to some of the Cin pin to the all the XOR gates and perform the XOR operation, and with B0 and carry, and you can give it to the input for the full adder. So the design code is our like this. So it's like module followed by module and end with end module. So here you can observe that full adder. So first we have to write the full adder code because we use full adders here. So that's why you have to instance this full adder code in the main code. So that's why you have to write this full adder code. So how you write module followed by module name. So followed by module name. And there are the input ports. What are our input ports for the full adder? For the full adder, the ABC are the inputs, and outputs are represented with output keyword. So it is our sum and carry. So assign sum. What is the formula for sum? In full adder, the sum formula is like AX or BX or C. For carry, A and B are means AB plus BC plus CA. The product is represented by AND operation, and the plus is represented by OR operation. So by using assign keyword, we assign the RHS value to the LHS side. So end with end module. It is our full adder code. We already discussed in previous videos, but that's why I explain here, means we use this here. So right, again it is our main. Now main one means what is our main one? Adder-Subtractor. Adder and subtractor code. So 4-bit adder and subtractor code. So it is our module and end with end module also here. So module followed by module name. So what is our inputs here? See, A. So how many bits are there? 4 bits. So that's why you can write input. So these are the inputs. So that's why represent with input keyword. Input 3 down to 0 means A of 3, A of 2, A of 1 and A of 0. 4 bits. So it will be a vector format. So input 3 is to 0 A, comma input. So second input is our B0, B1, B2 like 4 bits. So that's why simply represented with 3 down to 0 B. So if you want, you can represent like B0, B1. It's also like clumsy. So it is very simple format in representing the vector format. So third pin is our Cin or K. So in diagram, it represented with Cin or K. So that value is our enable pin. So why I mean en means it's like it's work like enable pin. So if it is enable, it going like subtractor. If it is not enable, it acts like a adder. So that's why I represented for easy understanding en. You can make it as a cin also. No worry about it. Output. So what is our output? Sum and the difference. So that's why for sum I represent S and for difference I represent D. So these are the output. So that's why I represented with SD out. You can represent with any name. So just for explanation I wrote like this. So another output is our carry. So here you can see these are the sum and the carry. So sum is 4 bits. So that's why I represent 3 down to 0 as D of out. So another output is our carry. So carry and borrow. So that's why I represent with CB out. So inside this connection means see here. So C0, C1, C2. So these are no operate means there is no storing purpose. So just it will drive the output to another input and this output to another input. So like that. So that's why we can take while. So no need of store any. It's not any input pin or output pin. It's just a wire which we are used to connect the interconnects between the code. So that's why I simply write while. So how many pins are used like a wire C0, C1, C2? So 3 bits. 3 bits means 2 down to 0. C of 2, C of 1, C of 0. So 3 bits. So you simply write like this. Full adder. So now you are going to instance this full adder code here. So how you are going to instance means we use full adder in the main code. See, it is a main design. So full adders we are using full adders. So that's why I have to instance the code here. So how you are going to instance? So followed by module name what you are going to instance. So I want to instance the full adder code. So that's why the module name what I wrote here is simply write this full underscore adder. You can give any instance name. So no need to be F1. You can write any name, your name also. So for a better, it is like full adder. So that's why F1, F2, F3 I wrote like this. But just remember that no, you don't use same instance name in below line. So if you wrote like this means it may make as a duplicate one. So you can use F1 in a test bench code again. But in the same code you don't use same instance name because it takes like a duplicate name and shows error. So don't forget about it. You have to use different instance name in the same code. So how we are going to connect? So see, for first full adder A0, B0 and our Cin is nothing but our enable pin and outputs are some S0 and C0. So I simply write here A0, B0. So what is our B0? So for a full adder the output is like B0 XOR K. K is nothing but our enable. So XOR gate in a Verilog code. So XOR gate will be like in a Verilog code it represents like cap. So that's why B of 0. B0 is nothing but B of 0 here XOR En. So our third pin is Cin again. So that's why En. So our sum S of 0 and C0. So now what is our second full adder going to be done? So see here. So it is our port connection. So how we are going to connect? It's by order. So what is your order? So in here we can see what is our order A, B, C, sum and carry. So these are the inputs. So these are the outputs. So you have to connect this A with A of 0, B with B of 0 XOR B of B0 XOR enable like that. C is connected to enable. So sum is connected to SD out of 0. So C carry is connected to C of 0. Like that we can connect by order. So if you want to connect by name then you simply write like this dot A of A0 comma dot B of, like that we can represent like dot A of like this. So it is like order. It is very simple to mention the order when there is a less number of input and outputs. If there is a 10 inputs and 20 inputs then it is not easy to connect by order. So it may be clumsy or you get confused. So that's why you can use there is a connection by name. So it is a very easy to don't mismatch any getting errors like that. So there is only 5 nearly 5. So it's like a 5 inputs and 3 inputs and 2 outputs. So total 5 pins. So that's why you simply use order. So second full adder. So see second full adder what is going to be done. So first input is A1, second input is B1. So it is not going to be B1. B1 XOR with enable again. So third input is our output of the first full adder. So C0 is our third input. So these are the inputs. So S1 and C1 are our outputs. So just see A of 1, B of 1 XOR with enable and C of 0. So like that we can connect the 4 full adders. So for third full adder, see A2 and the second input is B2 XOR with enable and the third input is C1 and we get sum and carry as the output. So like that we can instance every full adder here and connect the ports by order it is very easy to connect by order, means there is a less number of inputs and outputs, so that's why order is more preferable. If you have more number of inputs and outputs, you can go with the ports connection by name also. So after this you can stop with end module. So next, test bench code. So our test bench code is like, you don't write, there is a confusion between, for there is a 2 modules in design code. So for what code I want to write test bench, for full adder or Adder-Subtractor. So what I going to do means, just remember that what you are going to simulate. So what is our design, the main design or Adder-Subtractor. So that code only need our test bench code, so no need to write for the full adder. So just remember that. So inside this it will operate the full adder circuit also, so no need to write again the separate test bench to full adder. We simply write only our main code, a main module code, test bench only. So module and followed by module name. Here you can write any module name. Here according to code I written like this, so TB. And what is our inputs, it may give reg data type, and what are the outputs, it will be outputs will be a white data type. So mostly prefer, while you are going to write a reg 3 down to 0, A comma B, you think that both are 3 down to 0, so like that. But sometimes some of the compilers may getting error, because only A part will going to consider the 3 down to 0, so B is considered as only 1 bit, so A is going to be 4 bit. So sometimes the compiler will take, some of the compilers will take it as 1 bit, so the output will present only 1 bit, the remaining 3 bits are going to be assigned 0 as according to the inside compiler. So don't do that. You can write that data types in separate line, then you don't get any particular errors. So just remember that. So if you get any error, if you don't get, then no problem at all. So then you have to instance here. So instance here. So how you are going to instance over what for what design code you want to write the test bench code, you simply write that module name here. So add_sub, you can simply write. By this you can connect the design code and test bench code here. So followed by instance name, you can use any instance name. So mostly we prefer DUT, design under test. If why I write my name means, I just say to you, you don't need to mention only DUT, it is not a rule, you can use any name. So just for that only I mention my name. So there is a port connection by order. So A, B, EN and SD out. So means this port, these test bench pins. So what are the test bench pins are going to connect to the design code pins. So design code pins. So there is a initial begin. So initial begin, inside the initial begin we are going to give the different combination for the inputs. And in waveform we observe the output for the particular input combination. So when you are going to use the initial block, you make that what are the variables we are going to use in the initial block or always block, it must should be in reg data type. So that's why you always mention input ports with reg data type. So if you don't use any initial block, then you can simply use wire also in input ports. So every time I mention that. So when you are going, if anyone asks why you use reg only, why not wire means, so you simply say, sir, here or madam, here I use initial block. So that's why whenever you are going to use initial block or always block, you must represent the ports which are using in the blocks, it should be reg data type. So that's why I mentioned with reg. So if you don't use initial block, so no need to mention it as a reg, you can use wire. So say like this. So don't forget about that. So you can give ABC means enable pin, give different values. So see, first here I give sum, and the second I give difference. So third one again sum. So how I say it is sum, difference, sum, according to enable pin. If the enable pin is 0, that is going to be operated as addition operation. So it like a full 4-bit adder circuit. If the enable pin is 1, so it acts like a 4-bit subtractor circuit. If the enable pin is equal to 0, it acts like a 4-bit again adder circuit, like that. So give some delay between the different input combinations. So again you want to stop the simulation, we simply use the finish keyword and initial begin. So these 4 lines are used to generate the waveform in EDA playground. If you use Vivado, so don't need to no need to write these 4 lines. So if you are using EDA playground, you want to generate any waveforms for your understanding, you simply use these 4 lines. So I don't need any waveform, I do any Vivado tool like that, you no need to mention these all. So end with end module. So it is our test bench code. So after that you get the output waveform like this. So see here, these values are going to be represented here. So A value is equal to 8, B value is equal to 2, and enable pin C means C value is equal to 0. So enable pin is 0 means it acts are going to be as a sum. So means adder circuit. So 8 means 1 0 0 0, 2 means 0 1 0, and the enable pin is going to be 0. So again you can add, simply add. So what is like, it's like 10. So 10 is represented with A. So see, any carry is generated? No. So the carry will be going to be 0 and the sum will going to be A. So it is about adder. So what about subtractor means? So that's why I mentioned that waveform also. See, So it is, see, enable pin is equal to 0. In test bench code you write first 5 nanoseconds is going to be enable pin is equal to 0. Second, after that the enable pin means first it is going to be added as a adder, second it is going to be added as a subtractor. So that's why it is like second part. So it will act like a enable pin is equal to 1. So again enable pin is equal to 0. See, it acts like a subtractor. So what is the value here? A value is equal to A only, B value is equal to 3, enable C value is equal to 1. So now we are going to do this. So A means 1 0 1 0. So 3, see here, sorry, here we can done XOR operation here. So 0 0 1. So B is not directly take. So 0 0 0 0. So what is our XOR operation? XOR truth table 0 0, it is going to be 0 0 1, it is going to be 1 1 0, it is going to be 1 1 1, it is going to be 0. So 0 1 0 0. Again we get the same value of the B. So no need, so that's why you get correct answer. But remember that the second input is going to be A B XOR of enable pin. So now you are going to be B XOR with enable pin. Means B value is equal to 3 and enable pin value is 1. So 1 1 is 0 0 1 1. So 1 1 0 0. So here we can use enable pin also. You are going to be add. So you just use XOR operation according to XOR. So you use add only. No need to done subtraction. So it acts like a subtractor. You should use adder because there is no full subtractor you see in the. So there is all are adders. So inputs may be XOR operation. So you have to add this 1 1 1 0 1. So what you are going to do? So it is our output. So here we can see 7 and the carry will be generated. So carry borrow means borrow will be means. So it is act like a subtractor. So it like a difference. It is like a borrow. So you can simply write 1. So like that it operates like as adder or subtractor. I think it's up to now. It's I think clear. So if you have any doubts, you can comment on it about this adder or subtractor circuit. If you have any clumsiness or something, any particular line you don't understand, so just comment on it. I make separate video. So if you don't understand any waveform and operation and example, so you can say that also. I can make a short video for that. So thanks for watching and until then, bye.